Hi, my name is Matt Webster, and I'm the NDE team lead for the Luna Labs division of Luna Innovations. Today I'm going to talk about a technology that we've been developing over the past few years in collaboration with NAVC. It's called the Multi-Modal Sensitization and Stress Corrosion Analysis Tool, or M2SA. Luna Innovations is a small business operating out of Roanoke, Virginia. We're publicly traded, have annual revenues exceeding $60 million, and currently have approximately 460 employees spread over offices in Virginia, Georgia, Michigan, and California. Luna as a whole has two primary divisions, the Lightwave division, which focuses on fiber optic sensing, and the Luna Labs division, which serves as the R&D branch of the company and is tasked with identifying the next generation of commercial products for Luna Innovations. The Luna Labs division has more than 65 scientists and engineers over three groups: the Biotech group, which focuses on biosensors, wearable technologies, assays, and medical simulations; the Systems group, which focuses on asset monitoring, non-destructive evaluation, and data analytics; and the Materials group, which focuses on protective material coatings, gas separation membranes, and other things. This program is run out of the Systems group, which is building the M2SA technology from both an extensive portfolio of corrosion-related sensing programs and prior work with the Navy specifically focusing on monitoring sensitization levels in aluminum ships. The overall goal of this technology development effort was to produce a system that's capable of characterizing the risk of sensitization and cracking based on material-specific microstructural characteristics. These could include things like the level of cold working, the grain size, or whether the material is recrystallized or not. The main transition platform that we're targeting here is the littoral combat ship due to its extensive use of marine-grade 5000 series aluminum alloys in the ship's superstructure. And as such, we're seeking transition opportunities within PMA 501 littoral combat ships and PMA 505 LCS fleet introduction and sustainment. Our expectation in the end product of this that will come out of this development effort is something that will allow rapid, non-destructive evaluation of current sensitization levels and risk levels, a tool that is tailored to meet the specific needs of shipboard inspections, and a user interface that provides maintainers with actionable output of risk levels through the use of trained machine learning models embedded within the software. The sensitization problem is one that the Navy has known about for some time. It stems from the use of magnesium-strengthened 5000 series aluminum alloys in ship construction. And what they've found is that when these otherwise corrosion-resistant alloys are exposed to elevated temperatures, for example, baking in the sun during the hot summer months, the magnesium comes out of solid solution and forms precipitates that interact with the matrix material and cause intergranular corrosion, and under the right conditions, stress corrosion cracking. There are tools available to measure the level of beta phase in the material, in other words, the current level of sensitization, but it turns out that the rate of degradation can vary a lot depending on the material microstructure. To further complicate things, materials of identical alloy and temper designation can have wildly different microstructures due to the variety of processing steps that can be used to achieve that temper. In one study, multiple lots of the same alloy and temper were obtained from different suppliers and were found to vary in sensitization rates by a factor of 10. This highlights the fact that to truly predict the risk of sensitization, a tool is needed that not only reports the current sensitization level, but also takes into account the microstructure to predict that rate of sensitization. And the commercial opportunities for a tool like this, one that uses a non-destructive evaluation of the microstructure to predict material performance, are extensive. For example, in the metal production industry, it could be used to avoid the processing stages that would lead to a high rate of sensitization in aluminum alloys. There are also applications in the aerospace and automotive industries. Luna is addressing this need through the development of the Multi-Modal Sensitization and SCC Analysis, or M2SA tool. We built a strong team to approach this development, which includes experts in corrosion and stress corrosion cracking from the University of Virginia, and experts in the development of sensitization measurement tools at Electrowatch. We should note that Electrowatch produces the only other Navy-qualified sensitization measurement system, the DOS probe, and is also a subsidiary of Austal USA, which gives us opportunities for feedback from the aluminum ship OEM community. The M2SA tool leverages a suite of well-established non-destructive evaluation techniques to gather as much information as possible about the material microstructure. From ultrasonic sensing, information about the elastic properties and grain structure can be gained. From eddy current sensing techniques, conductivity changes due to sensitization can be detected. And a portable X-ray diffraction unit gives information about the crystallographic texture and recrystallization status of the material. All of this information is fed into a user interface that automatically extracts metrics of interest and uses these as input into machine learning models trained on inspections of materials with known microstructural characteristics and sensitization behaviors. The M2SA system provides users with a non-destructive assessment, is capable of being transported and used by a single person, it's hardened for use in a naval environment, and provides actionable results in about an hour. We began the development of the M2SA system in 2018 under a Phase 1 STTR contract. In the Phase 1, we demonstrated the ability of the individual sensing modes to detect key microstructural features during lab measurements, and also gained information from the research community about which microstructural features were most important for predicting the sensitization behavior. We just completed the base period of our Phase 2 STTR contract, and in the Phase 2, we focused on developing an extensive material library that we could use to optimize the sensing techniques and to produce a database of material responses for machine learning model development. We completed a working prototype of both the hardware, the software, and the machine learning models for the M2SA system in late 2021, and are awaiting a funding decision for the Phase 2 option. During the option period, the performance of the prototype will be evaluated on both the laboratory coupons that we built up and through shipboard measurements with partners at Austal. The option will culminate in a TRL-6 Navy demonstration of the technology and detailed plans for qualification and commercialization of the unit. Once fielded, the M2SA tool will provide immediate benefit to Navy customers. For example, to alleviate the problem of using high-risk aluminum alloys for ship construction, the M2SA tool could provide a quality control step that results in reduced lifetime maintenance costs. And to alleviate the problems of operational efficiency and mission readiness due to ship maintenance from sensitization issues, the tool could provide users with improved information that would help optimize scheduling and reduce downtime. And for improving upon the problem of material suppliers using processing steps that lead to materials that sensitize more quickly, the tool can provide them with process optimization and feedback to reduce the production of problematic materials. Luna will draw on more than a decade of experience in sensor development to deliver these benefits to the Navy. Ultimately, the portability, non-destructive nature, and intelligence of the M2SA system improve upon the available solutions, allowing inspection of internal structures and improved prediction of future risk levels. For any non-destructive evaluation tool, reliability is key, and qualifying the reliability is an important step for qualifying for use in the field. Unfortunately, this often falls outside of the scope of even a Phase 2 SBIR or STTR program. For the M2SA system, reliability testing needs to include extensive testing on shipboard specimens to capture the full range of expected microstructures. This is something that we started working on in collaboration with Electrowatch and Austal, but more specimens are going to be needed to fully qualify the system and to improve the predictive models that we've built up. There's also a need for human factors testing and service environment testing to make sure that the system has the form factor that meets the MIL standard 1472H criteria and that it's robust enough to survive in a naval environment. Our expectation is that a sequential Phase 2 or Phase 2 enhancement will be needed to achieve these qualification steps, and that low-rate production will begin in a Phase 3 following qualification. Our need from the Navy community is first and foremost a transition advocate and technology champion, essentially people that see the need and the benefit of this technology and are willing to work with us to push past the hurdles toward commercialization. A transition advocate and program of record will also help us to streamline the process by identifying the specific tests needed for transition targets that are most important to the Navy. They will also serve as the monitor and approval authority for the qualification process to make sure that the M2SA system meets the Navy's needs. Like I've already mentioned, there are a lot of different markets that could benefit from the M2SA technology. We're currently engaged in market research to identify and target specific market segments. As part of this, we in Luna Labs have conducted qualitative exploratory research of the material production, shipbuilding, and NDE markets to identify specific problems. We've worked with our internal marketing specialists to quantify the addressable market size and have consulted with customers and end users to refine the product requirements and business models. In addition to the initial Navy market, we firmly believe that the novel ability to non-destructively examine a material's microstructure and to apply that information to performance prediction models will benefit material production, aerospace, automotive, and shipbuilding industries. As we move through the market analysis process, we're looking to identify early adopters in each of these areas to broaden the customer base. This also includes examining other DoD services that use aluminum platforms or otherwise have microstructurally driven issues that need to be addressed. Ultimately, we can only go so far with this development without support from a program of record. As you can see in this development timeline, only the early stages of identifying transition advocates, prototyping, and low-rate production can be achieved using Luna's capabilities alone. By adding support from a program of record, we would be able to gain a better understanding of the qualification and transition process and would have better access to the funding needed to complete these critical steps. The result of this would be the deployment of a first-in-kind microstructural-based sensitization risk assessment tool. From the momentum gained from this important milestone, we would be able to attract manufacturing partners to scale up production and extend deployment to other Navy ships or other DoD assets. What we want to know as I wrap up this presentation is how can the MS2 tool work for you? We're very interested in hearing about your specific needs and how we can address them. For more information about this technology, you can contact me or my group director, Marcus Grimes, using the information at the bottom of this slide. Thank you.